The bagpipe is one of the oldest instruments. To play it, you blow into a pipe attached to a leather or synthetic bag, then press on the bag to force the air out through other pipes to create sound. You transform this sound into a melody using finger holes on a reeded pipe called a chanter. They start by carving a 20-centimeter long block of wood, rounding it to a diameter of 4.5 centimeters. It's part of a drone, one of 3 on the bagpipe, that create bass and tenor harmonies. They drill a hole that will later become an air channel. Using a lathe and a plastic template as a guide, a craftsman spins the wood to carve it, a process called turning. The lathe has a stationary carbide-tipped cutter, strong and precise enough to cut this hard African blackwood. It's a very heavy and dry wood, perfect for turning. For more intricate decorative cuts, he uses a handheld device called a combing tool. Next, he uses what's called a parting-off tool to make additional decorative grooves. He measures these grooves using a caliper to ensure they meet the specifications of the design. The craftsman drills a hole to create what's called a projecting mount. It's made of imitation ivory and at 5 centimeters in diameter, it fits on the drone like a washer, but it's just for decoration, one of 7 on the bagpipe. He adds a metal component called a slide, also for decoration. Next, he turns what's called a blowpipe. This one's made of plastic to withstand moisture from saliva. Traditionalists prefer blowpipes made of wood. He adds a mouthpiece. It retracts by 20 centimeters depending on the player's height. The player blows into the mouthpiece to inflate the bag. A small metal tube between 2 plastic blades forms the chanter reed. When air strikes it, the reed vibrates inside the chanter, a pipe at the bottom of the instrument that has 8 finger holes for notes and 2 for pitch adjustment. To secure it, the craftsman wraps the reed with hemp string and winds Teflon tape over the string for an airtight seal. Then a brass wire called a bridle to control the shape of the reed. Narrowing the opening produces a higher-pitched sound. The craftsman ties hemstring to create traction between the drone segments, holding them together. Hemstring is especially durable, yet easily replaced if damaged. Here's the completed tenor drone. Next, a craftsman inserts what's called a stalk through the zippered opening of the pipe bag. The pipe bag's made of synthetic, breathable material. The 5 stalks fit through a rubber collar in the bag, attaching to the 3 drones, the chanter, and the blowpipe. The craftsman inserts the chanter through a sleeve in the bottom of the pipe bag. He secures it with string, tightening it around the bag. He closes the zipper to form an airtight seal. Next, he places the pipe bag into a decorative velveteen bag cover. He inserts the stalks through holes trimmed with wool or silk fringe. A rubber valve prevents the player's air from coming back up through the blowpipe, channeling it through the chanter instead. Another part, called a drone reed, acts like a plastic tongue. It vibrates over a long hole to create the bagpipe's humming sound. The craftsman inserts the drone reed into the drone and then into its stalk. Wool cords keep the drones in place while the player plays. Finally, the craftsman fits the chanter reed into the chanter, then slides it into its stalk. A bagpiper must have a strong set of lungs because some songs can run for 20 minutes. Now that's long-winded. Lapel pins let you proudly show off where you've been or where you stand. From an event you've attended or your political beliefs to your professional affiliation or your favorite sports team. Lapel pins cost pennies to produce, but some are collector's items worth thousands of dollars. They may be tiny, but they're out there in huge numbers. This one company turns out about 5 million lapel pins a year. It all starts with a sketch of the pin design, and from that, the master, a negative made of magnesium, a type of metal. They'll make copies of this master to create a production mold. But first, using what's called a coping saw, they cut out the front and back pieces of the master. Using a dispenser about the size of a sewing needle, they glue the pieces together with epoxy. It takes 5 minutes to dry. Then they cast enough copies of the master to fill up a rubber disc. After tracing the outlines, a worker uses a surgical knife to meticulously carve out the cavities. He softens the rubber with paint thinner to enable precision cuts. Then he places a copy of the master in each cavity. Another disc goes on top. Then it's into a machine called a vulcanizer for 1 hour. This machine uses heat and pressure to cure the rubber, making it as hard as a car tire. It also melds the rubber around each master copy, embedding the detail. This will be the production mold for producing this pin design. Now, using a surgical knife again for precision, they carve out sprues, channels that during the casting process will direct the flow of molten metal to the cavities. They also make smaller, curved channels called runners to filter out any air or dirt particles. It's crucial to position the sprues and runners correctly because this mold produces an entire line of a particular pin. Mess up and they'd have to remake the mold from scratch. Next, they insert a centimeter-long brass tack called a post into each cavity. It'll later fasten to a clasp, attaching the pin to clothing. The post goes in now rather than later so that it will fuse to the back of the lapel pin during casting. Now to close the mold, they align the buttons on one half with the depressions in the other half. The mold then goes into what's called a spin casting machine. Using a cast iron ladle that can withstand the fiery temperature, they pour in molten metal, either pewter, zinc, or a tin alloy. As the machine spins, centrifugal force propels the metal into every nook and cranny of the cavities. After a minute of spinning, 400 rotations, the mold comes out. The metal takes about 5 minutes to cool and harden. The factory remelts the excess metal for the next batch. Next, a brass clasp called a clutch goes onto the post. Now the lapel pins go for an hour-long wash in soap and water and abrasive stones. The stones smooth out any rough edges. The pins go into the electroplating tank for a surface coating of metal. How many coats and the types of metal vary with the design. An electric current draws the metal particles onto the pins, plating them thoroughly. These pins first get copper plating, then nickel plating, then gold plating. Now it's time to paint the lapel pins. Workers follow a numerical guide like a paint-by-numbers kit. They paint each pin individually using minute quantities of epoxy paint. They control the paint syringe with a foot pedal. Once the paint dries, a machine called a pad printer gathers up ink and stamps on the tiny details, the ones too small to paint by hand. Pierce the post through the fabric, secure it with the clutch, and this lapel pin is now ready to wear.
Fabric is made from thousands of braided threads. This mill has 700 bobbins of polyester. Each bobbin contains 250,000 meters of thread. We begin by separating the threads. This warp unit takes the 700 strands and assembles them. Then this comb separates them. Other strands are added, and in total, there will be 7,000 of them well aligned. One fabric is composed of threads braided at 90 degrees. The warp threads are assembled lengthwise, while the weft threads are joined transversely. To prevent the threads from tearing, they pass through a bin of glue. These rollers eliminate the surplus. The glue will be removed with water before dyeing the threads. The glued together threads exit this machine. These large green cylinders are heated and dry the glue on the threads. Knitting will soon begin. The 700 strands are newly separated on this loom roller. Each thread must pass through a blade to produce a specific design. This machine takes the 7,000 strands of thread one by one, and they pass through the blade. It's a highly precise operation. The threads pass through a blade, and the weaving finally begins. On this Jacquard-type loom roller, the warp thread is inserted by a jet of air. The weaving machine assembles two loom rollers made of 7,000 strands. The fabric reaches a width of 3.65 meters. The dark threads are inserted into the weave. They insert 600 weft strands per minute. The blades remove the weft strands to insert the warp ones between the two. A comb pushes the weft. The plate of the breakage chain stops the machine should a thread break. This bobbin contains 250,000 meters of thread. That's 250 kilometers. The weft thread is in the insertion nozzle. When a weft is inserted, an air jet nudges it in. The loom roller operates at full tilt. It makes 600 thread intersections a minute. Weaving is now over. We move on to the following steps: washing and dyeing. Washing is done in a soapy solution at 80 degrees in a continuous manner at a speed of 60 meters of fabric a minute. The fabric is rinsed in clear water of about 30 degrees. Now it's on to dyeing. This is done with jets. Up to 12,000 meters of fabric are placed in clean water into which colorants have been added. The solution is heated and the fabric soaks here for about 6 hours. Then it will be rinsed in lukewarm water. The fabric is placed in a bin. This machine is called an opener. It unfolds and stretches the material before rolling it up on an immense roller. And now the roll is almost full. We now move to thermosetting in a high-temperature oven which dries the fabric. The temperature is 200 degrees centigrade at the oven's entrance. The fabric circulates here for 45 seconds. This finished roll weighs 1,500 kilos. The bobbin that we saw at the beginning has produced 25 kilometers of fabric. It takes about 90 minutes to assemble a computer. Its hard drive disk saves information transmitted to it for a long time. The reading head reads the information. It is extremely precise. The space between the reading head and the hard disk is as thin as a hair. The hard disk is installed in its position within the computer. There there are two other units which safeguard information: the removable 3-inch disc reader and the CD-ROM reader, which allows for the reading and execution of programs recorded on compact discs. These two units are placed into position. The spinal column of the computer is the motherboard. It is to this unit that the other elements of the computer are connected. This cooler dissipates the heat generated by the chipset. Certain sound cards are integrated directly on the motherboard. These connections, in sequence, are the audio input, its output, and the microphone port. This AGP retaining ring secures the video card during transport. This thermal unit measures the temperature emitted between the processor and the motherboard. The processor is the brain of the system. It interprets, calculates, and executes the instructions given to it. The processor has several millions of transistors, and its cadence, its operating speed, reaches the gigahertz level. The processor rests on this base. The processor's cooler dissipates the intense heat. Its efficiency depends on the type of material used, and a conducting material assures better cooling. The RAM memory stores short-term information, but erases it when the current is turned off. This memory is more rapid than that of the hard disk or the CD-ROM. Now they integrate everything in the case. It protects the internal elements from the external elements. At this stage, they install the electronic components in this case. Several connectors of the case are connected to the motherboard, such as the commutator and various light indicators. This is the output connection for the video card, which links the computer to the monitor. We also see the video chip, which creates images in 2 and 3 dimensions. Here is the video memory. The more its capacity is increased, the clearer will be the image displayed on the monitor. The video card is placed into its position. The modem allows two computers to communicate. Its condensers produce the perfectly clean phone signal to facilitate communications. These modem chip connectors control information circulating between the two computers. The fax modem is installed. The power supply transforms electricity according to the voltage required by the different components. The computer's interior cabling is installed. It allows information to travel between the different media and the motherboard. The IDE cable is connected and the CD-ROM. The last electrical wires are connected to different computer components. The assembly of 30 components of the computer is now finished. Just before closing the case, they test each computer to verify the good functioning of the peripherals. Then they close up and proceed to packaging. This company produces about 300 computer units every day.